it is rather than switching back and forth between the two cameras in this system, I'm going to be sharing my screen, which shows the other camera. That way, hopefully, you'll be able to see both cameras at once. You'll be able to see the other camera full screen. You'll be able to see this camera as a thumbnail. So we'll see that. I'll see if that's going to work. Let me try doing that right now. It worked when I practiced it. Okay. So now I should be sharing my second camera, which is on a tripod here, so you can see better what's going on. So I just have a blank sheet of paper. Underneath it is a piece of cardboard that'll allow me to push pins through the paper into the cardboard. So can everybody see that?
Yes, I can see it.
Okay. Is it full screen for you?
Yes.
And then I'm a thumbnail in the corner?
Yes.
Okay, cool. That's the way I was hoping it would work, but I'm still kind of new at this stuff as well. I'm still learning.
Yeah, I don't know much about this either. I'm like, okay, I guess.
So in some cases, I'll have to disconnect this from the tripod, just hand hold it. But for now, I'm gonna try using the tripod so I can have both hands free. So the first thing I'm going to be doing is we're going to be looking at reflection and refraction. Now we talked about reflection and refraction earlier in the semester, so this might seem like a weird time to be doing it, but that's just the way the scheduling worked out for doing these labs. So here, it's not really in focus. Hello, focus. Sometimes it takes a little bit of effort to get this thing to focus good. So here I have a piece of glass, and we're not going to be looking through it like this. We're going to be looking through it edge to edge. So you can see two of the, whoop, no, you can't. Two of the sides are frosty, so we're not going to be using those. And two of the sides are clear, so we're going to be looking through the glass, through the long side to see refraction. First thing I'm going to do is put this on this paper. Wherever the background noise, we need to mute the mic if whoever's got that going on. Okay, so first thing I'm going to do is I'm going to trace my glass on the paper. So if I have to pick it up, I'll know where it was. I'm using black pen, which hopefully will show up on the camera good enough. Okay, so I've just made an outline of the glass so I can move it and put it back, and it's always back where it was. Now, the second thing I'm going to do is I'm going to take just a straight pin, and I'm going to stick it on the far side of the glass. I'm going to take a second straight pin, so that one we call pin 1 in your handout. Then I'm going to take the second pin, we call pin 2, and I'm going to put that one behind and a little off to the side of the first one. Now what we want to do is we want to figure out the path of light as it goes from one pin to the other, then through the glass, and then out the other side, because we expect it to bend as it goes through the glass. In order to do that, we have to look through the glass. Now I practiced this with the camera and it worked okay. I'm going to try this and see how it does. So I'm going to take the camera off of the tripod, and I'm going to take it down here to table level. And so hopefully what you should see is the pins through the air up here, but then you should also be able to see the pins through the glass down low. Can you all see that? Let me try to get the camera a little lower. All right, so you see the pins through the glass, and you see the pins through the air. Now, what you'll notice is when I move back and forth, they don't move the same, right? Because one is looking through the glass, and so the light is bending differently than seeing the pins through the air. And so I'm going to move my camera until the pins line up in the glass. Now you notice they don't line up in the air, right? They're still not lined up in the air. But down here in the glass, down here in the glass, the pins are lined up. So I'm going to take a third pin, we call it pin 3, and I'm going to put it up against the glass where it lines up with the other two through the glass. Best I can. There we go. Right, so now you see there's the 3 pins, and they should all line up. So they should all line up like that, right? Now I'm going to take a 4th pin and line it up with the other 3 away from the glass on my side. Let me get it back off a little bit more. So get those 3 lined up, and then this one lines up with those 3. And honestly, I'm just using the camera view as well as you because I'm not bent down. Normally I'd bend my eyeball down to table level and do this with my eyeball. So there you can see all 4 pins are lined up, right? If I go off to the side, you can see all 4 pins, and then they all fall on top of each other, just like looking at a line of fence posts edge on, right? It's all line up with each other. What that means is, as far as the light is concerned, it's a straight line, right? Because they're all lined up. But we can see from the other 2 pins in the air that the light isn't following a straight line relative to the air. So I'm going to go back to the tripod here so I can use both hands again. And it'll take me a second to get this reset. Hang on. All right, so now you can see more of a top-down view of what this looks like. Now I can remove the glass, and the 4 pins show me the path of the light. And if I take a ruler, I can connect the lines between the pins with my like that. And what you see, hopefully, is that the light path isn't straight. Let me do more of a top down here. So you should see the light went from these 2 pins, and then it bent right at the glass, went in a straight line through the glass, and then it bent again and came back out of the glass. And so what we want to do now is measure those angles so we can figure out how much it bent. And by measuring the angles and using an equation, and I'll show you in a little bit, we'll be able to calculate the index of refraction, which is basically a measurement of how much slower the light is going in the glass than it was going when it was in the when it was going through the air. Now, another thing I can do that I didn't show you before, but I'll go ahead and show you right quick, is with the glass in place, you can double check this bending with a laser pointer. So this is a green laser. And so if I line up the laser with the first 2 pins, you should see that the laser line, I have to tip it back and forth. The laser line follows that path and hits the second 2 pins as well. Doesn't show up quite as well on the screen as it does in person, but you should get the idea. Try to get the laser down at table level. So I should be able to get the laser light to hit all 4 pins. All right. So now I can remove the pins because I've marked everything, and I'm going to find the line that's perpendicular to the surface of the glass. That's called the normal line. And so I'm going to start from where my pin was, and I'm going to make a dotted line on either side of where the glass was. And this is called my normal line. This is what I measure my angle relative to. I'm not measuring the angle relative to the surface. I'm measuring the angle relative to the dotted normal line. So I can do the same thing over here. And we see that we have a normal line for each interface. So now I'm going to use my protractor. It's a tiny little protractor, but it works better for these smaller lines, so because they're not extended very far. I still may have to extend some of them a little bit, just so I can see where it hits on the protractor. I can extend those lines a little bit. Sorry, it's gone out of focus again. Focus. Never quite sure how to get it to refocus, but hopefully here in a second it'll figure itself out. So everybody see what I've done, right? There it goes. I've got the dotted lines at each interface with glass, and you can clearly see that we bend towards the normal from air to glass. We bend away from the normal from glass to air. We're going to measure all 4 of those angles. And so I'm going to label them as I go, according to the way they're labeled on your worksheet. So first of all, I'll label the pins. That was pin 1. That was pin 2. That was pin 3. And that was pin 4. And so at pin 2, we're going to measure these angles. The one in air called the incident angle, so it's I2. The one in the glass is the transmitted angle, so we call it T2. And so I know maybe in a little while since some of you used a protractor, we're going to line up the 0 of the protractor with our dotted line, put this little black dot right where our pin was, and then we read right here what this angle is. And it looks like, I don't know how well you can see it from where you are, but it looks like it's about 26 degrees. I'm going to label that as I2 equals 26 degrees. So that's the first number you need to put on your worksheet, is that I2 is 26 degrees. If I can get this a little bit closer. The second angle I'm going to measure is this transmitted angle. So I have to flip this around the other way, put the dot on the same point, line up the line, the 0 line with the dotted line, and then I can see that it is now almost 20. So I'm gonna call it 19. So this is 19 degrees. So T2 is 19 degrees. And then I'm going to measure this transmitted angle at pin 3. So I put this where the pin was, and I line up the dotted line with the 0. And I see that it is also 19, which is normal. When you're using something that's square like this, we expect things to be pretty much symmetrical. So it doesn't always work out that way, but today it's working out where those 2 angles are the same. So we expect this angle to be similar to our 26. It may not be exactly, but we expect it to be a similar number. So line this up like that. And okay, it's a little bit bigger. So it's 25, 26, 27, 28. So this one's 28 degrees. So I3 is 28 degrees. So those are the 4 angle measurements that you should have on your worksheet. Let me get a little bit closer by detaching the camera. So we have at pin 2, an incident angle of 26 degrees and a transmitted angle T2 of 19 degrees. And then at pin 3, we have a transmitted angle T3 of 19 degrees, and we have a incident angle I3 of 28 degrees. So those are the first 4 angles that should be on your worksheet. Now the rest of step 1 on the worksheet are calculations. So I am not going to do them, but I'm going to show you how to do them. So the first thing it wants you to do is to calculate the index of refraction. Now, in order to calculate the index of refraction, what we're going to do is we're going to use an equation where this is the sine, which is the geometric function of sine. Most of your calculators should have a way to do sine. Make sure you're in angle mode on your calculator in order to calculate a sine. Don't worry about what a sine is because you can take a geometry class for that. So it's going to be sine of the incident angle over the sine of the transmitted angle. So for my first example, I'll go ahead and set that one up. My first example, my angles are 26 and 19. So my first n, that's called N2, because it's pin 2 on your worksheet, is going to be the sine of 26 degrees divided by the sine of 19 degrees. As long as your calculator's in degree mode and you do the sine of 26, that just gives you a number. It should be a number between 0 and 1. And then you get a similar number for the sine of 19. Divide those two numbers, and that should give you your index of refraction. Now, your index of refraction should be a number that's bigger than 1. 1 is the index of refraction for air and for a vacuum. And so since we're going slower in glass, we should have a number that's bigger than 1. It should be less than 2. So your n should be bigger than 1. It should be less than 2. If you don't get a number between 1 and 2, then you've probably done something wrong. Probably you're in radians mode, or you just did the algebra wrong somehow, dividing those two signs. So the next thing that you're going to be, so you do that twice. Do that for the first set of numbers, and you also do it for the second set of numbers. I'm not going to fill it out, but it looks the same to do N3. And then I want you to find an average. And of course, hopefully everybody remembers that if you want to do an average, it's just going to be, you add the two numbers together and you divide by 2, right? And so that's going to give us the average n. And then the last one is calculating the speed of the light in the glass. Now, the calculation for that is, we know that the index of refraction is also equal to the speed of light in a vacuum, c, divided by the speed of light in the glass, which is v. And so we have to algebraically solve this equation for v, which is a little bit more complicated than usual because the v is on the bottom, right? And so the easiest way that I solve it, and you can do it different ways, is you can multiply both sides of the equation by v, right? Because multiplying anything you do to both sides, you don't change anything. So you multiply both sides by v, these v's cancel out, and we end up with nv equals c. Now we can divide both sides by n, and these n's cancel out, and we get that v is equal to c over n. Now, normally I make students do that algebra themselves, but since we're remote and it's going to be hard for me to check your algebra, I'll go ahead and demonstrate that. So now that we have v as a function of c and n, we can plug in our numbers. So n is going to be the average n from here. C is just going to be the speed of light, which we know is 3 times 10 to the 8th meters per second. And we're going to divide that by our number that's between 1 and 2. And since we're dividing by a number bigger than 1, we'll get a smaller answer, right? Now, it's still going to be a big number. It'll probably be 2 point something times 10 to the 8th meters per second. So it's still going to be a really big number, but it won't be as big as this number. Okay, any questions so far? Okay, I'll take your silence to mean everybody's with me. But don't be shy to unmute and ask a question if you're lost. So that's finished part 1 of our refraction. Now the second thing we're going to do is we're going to do it all over again. But this time we're going to have a triangular piece of glass. So I've got my triangular piece of glass. And the first thing I'm going to do, just like before, is I'm going to trace it out. Okay, so I just muted whoever was making that racket. So now that we've got our triangular tracing, right? So we can move the glass if we need to, or if it gets bumped. We're going to do the same thing with our pins. So I'm going to take a pin and put it right next to the triangular piece of glass. I'm going to take another pin and put it kind of off at an angle to that. And then I'm going to take my camera. I'm going to get it loose from the tripod. And I'm going to get down at table level, just like I did before. And I'm going to try to see those pins through the glass. Okay, so there they are, right? So we see them through the air. We can also see them through the glass. Now, are we seeing both of them, though? Oh, there's the other one. It's hard to see sometimes with this one. This one's harder. Harder to film, and it's also harder to. I'm running out of room on my cord here. I'm gonna have to shift over a little bit. All right, so you can see where my computer there is sitting up on a potato chip bag, or box. They're not focusing good, but there's the two pins through the glass. You can see them separately. Then I can move over until they're on top of each other, right here. I'm hoping it'll focus here in a minute better. So I'm going to take my third pin. Problem is it's focused on that potato chip bag, the box. There, that's better. So there you see the two pins, right? Two pins separately, and then we get them till they're lined up. And I take my third pin and line up with the first two, right? So they're separate. Now they're on top of each other. And I take my fourth pin and line it up with the other three, like that. So if I look at my top-down view, rotate this so I can see it better. I see my four pins, and they clearly don't follow a straight line at all, right? And just like before, I can take my laser, and I can get my laser and shine it on the first two pins. And you see that you can see the laser as it bends the first time, it goes through the glass, and then when it bends again, going out of the glass, and follows the four pins. Now, the other lines you can see are internal reflections and stuff off the surface, so don't worry about those. But you should basically see the path of the light as it goes in one side and it bends at both surfaces and out the other side. Okay, so now I'm going to put this back on the tripod so I can draw my lines. I get rid of the glass and use this as my straight edge because it's shorter. So I'm gonna connect those two, connect those two, and then I'm gonna have to get rid of one of these so it doesn't get in my way, and connect these two. All right, so my pin was quite at the edge, so I extended that line so that the top line is the good one, the bottom line is the bad one. So now I'm going to do the same thing I did before as far as getting my normal lines. So I find my dotted line for this surface. Well, notice that we're staying perpendicular to the surface, but now they're not going to be parallel to each other, right? Because we've got a triangular piece of glass instead of a square piece of glass. Okay, so there's that. So now I can measure. Well, first let me number my pins. So I'm going to number them 1, 2, 3, 4. We'll rotate this so you can see it right set up. All right, so there's my 4 pins. And now I'm going to start measuring my angles. Again, I always measure the angle relative to the dotted line. And this first angle is almost going to be 60. I'm going to extend it a little further so I can see it better. I'll go ahead and extend this one while I'm at it. If you put the pins too far away, they're hard to see, but if you put them too close, then you have to extend the line to measure the angle. So it's a trade-off. All right, so line up my protractor, and I can see that, let's see, that's 60. I'm not quite there. Maybe I am. Which one's 60? Okay, that one's 60. So it looks like I'm going to call it 59. So again, we use the same numbers scheme as we did before. So this is I2 is going to be 59 degrees. Now measure from this side my transmitted line, or transmitted angle. And I'm going to have to extend it a little bit too. So that one is going to be, well, there's 30, there's 35, 34, 30, looks like 33. So this is going to be T2, which is going to be 33 degrees. And so I had to write it small because I don't have a lot of room here. I'll zoom in a minute. And then on the other side, for pin 3, I need to extend this line the other way. This one gets a little messy. So line that up with the 0. And it is going to be 25, 26, 27. So I'll write it down here. T3 is going to be 27 degrees. And then my last one, my I3, is going to be over here. And that one is just past the 40. I'm going to call that one 41. So I3 is going to be 41 degrees. So notice in this case, the angles are pretty different from each other because unlike the square, things won't necessarily be symmetrical in this case. And so I've got T2, I2 is 59, T2 is 33, T3 is 27, and I3 is 41. Now you're still going to do all the math exactly the same. It'll be sine of 59 over the sine of 33 equals 1, your first n, n2, and then sine of 44 over the sine of 27 will give you your n3, then you average them, and then you calculate a velocity from those. And so I'm going to leave the calculations for you guys to do, but that's all the data that you need from this one. Now, the good news is the other two parts of this section of the lab go really fast. So I'm going to get a fresh sheet of paper. And we don't need the cardboard anymore because we're not going to be pushing pins. So I got a fresh piece of paper here. And I'm going to start out with my flat mirror. So I've just got a flat mirror. See, you can see the camera and the mirror there. So my flat mirror is going to go here. Just going to lean it up against this box, hopefully. And then I have this guy. This is a light box, and you may recognize it. We used it when we did the lens lab. Remember, it had this thing on it we used for the lens lab. But today I'm using the end of it here. That can give me 1, 3, or 5 parallel lines of light, or it can do red, green, blue colors. So I'm using the one line first for part 3, and I'm going to turn this on. And so we see the line. Now, so this is the incident line. In the mirror, you see a reflection of that, but that's not what we're looking for. We're looking for the reflection on the paper. And if I tip the mirror up a little bit more, you can see that better, right? So I think the instructions may say to push pins, but I'm just going to make marks with my pen. So there's the incoming light. There's where it hits the mirror. There's where it reflects off the mirror. And there's where it's going past the mirror. I'm also have to draw the surface of the mirror, because that's still that's still important to calculate my normal line. And so you see the light from the light box goes in, hits the mirror, then bounces off, right? You can also do this with a laser, but in this case, it's a little bit easier to see with the light box. So now I can get rid of the light box and get rid of everything. And I'm going to use my straight edge to connect these lines. So this is my reflected ray. And this is my incident ray over here. So incident, reflected. Now I have to find a normal line, just like I did before. So I'm going to find the line that's perpendicular to the surface of the mirror. And now I'm going to measure my incident angle I and my reflected angle R, and we'll see what those guys are. So my incident angle, line up my zero line with the dotted line, put the point there where hit the glass or the mirror. Actually, it wasn't a glass mirror, it's just a steel mirror. There was just a piece of polished metal. And we can see that I'm right at 40 degrees. So my incident angle is going to be 40 degrees. My reflected angle, if I measure that one here, and it is 39 degrees. Now, the law of reflection says that the angle of incidence is equal to the angle of reflection. So ideally, these should be exactly the same. But because of experimental error, they're not exactly the same. So on your worksheet, it's pretty simple. You fill out 40 degrees for the first angle, 39 degrees for the second angle, and the percent difference is going to be the percent difference between the two numbers. Now, just to remind you, how do you find the percent difference? It's going to be the difference between the two numbers, in this case 1, divided by the average of the two numbers. In this case, it'll be 39.5, right? Because you add this together, divide by 2, you get 39.5. So 1 divided by 39.5 times 100 degrees that's going to give you your percent difference. It'll be fairly small, but not tiny, but it's certainly acceptable. All right, so the last thing I'm going to do with this part of the lab is my curved mirror. Now this one's even more simple than the other mirror because there's really not that many things to measure about it. What we want to see and observe is how parallel light rays are affected by a curved mirror. Remember, this is how our telescopes that use mirrors work, is by having a curved mirror. So you can see, hopefully, that these parallel light rays come in, and then the curved mirror make them all come to a point. Now, you can also see that if you go too far off to the edge, see how they start splaying out and it doesn't really work? That's called spherical aberration, because this is actually a part of a cylinder, right? So in one dimension, it would be the same as a sphere, a circle. And rather than a parabola, it should really be a parabola shape. But it's not really a problem unless you get towards the edges and really high angles. If you're centered up, then you can see that it comes to a point pretty well. And so a lot of times, even professional grade telescopes will use spherical mirrors rather than using parabolic mirrors, because it's just so much cheaper to make them. Let's see if I can put this down here. So I'm going to trace out the mirror. And the instructions say you should mark all the lines, but in the interest of time, I'm not going to do that. I'm just going to mark the point or the distance where they all come together. So everybody see that? I marked where the mirror is. Come on, focus. Here we go. I marked where the mirror is, and I marked where the focal point is. So now I can remove that, and I can get my ruler. I'm going to use the metric side of my ruler, and I'm going to measure how far it is. So we can see that it's a little over 2 centimeters. That looks like what, the third mark? So 2.3 centimeters is the focal length of my cylindrical mirror. You can see the camera again. And that's the only thing we have to put down for part 4 there. It's just the focal length in centimeters. So that means we're done with the first half of the lab. Now there's going to be a little bit of a changeover, because the other part of the lab is over there on a different table. And so I'm going to have to move, hopefully without messing anything up. We'll see how well this works. Okay, I'm going to unplug my computer. Hopefully it's got enough battery power to last me the rest of the way. Come on, Velcro. All right, hope I didn't make anybody sick just now. So now we're going to be doing this other lab, which is all about the intensity-distance relationship of light. Now, before I actually start talking about this one, or start doing this one, I've prepared a little bit of a presentation. I'm gonna stop sharing that camera view, and now I'm going to share a PowerPoint instead. Okay, so you guys seeing the PowerPoint now? Somebody unmute and say yes or no.
Yes.
Okay, good. All right, so I stole some of these slides. They're kind of rehashes of what's from a couple of my lectures. And normally I just do this on the whiteboard, but obviously it's not going to be very useful today. And I left my pen at home, so if I have to draw anything, I'll have to use my finger. So I don't know how that's going to work, but we'll muddle through. So what this part of the lab is all about is the fact that light gets dimmer with the square of the distance. And so here's an image that was in your book, and it was also in one of my slideshows, where you can see when you're at 1. Let's see, I think my pointer. You guys see my pointer, right? Moving around. Y'all see my pointer?
Yes.
Okay. I thought so, but I never quite sure what you guys are seeing and what just I see. So you see there was this light bulb. If we're 1 unit away in radius, then the light from that part of the light bulb has to cover that 1 square unit of surface area of that sphere. But if we go twice as far away, so we're 2 units away from the light source now, that same amount of light from that same part of the bulb now has to cover these 4 square pieces of area, right? So it's 2 by 2 compared to what it was before. And so 2 by 2 is going to be 4 times the area. And so that comes from the fact that the area of a sphere is 4 pi r squared. And so as the radius increases, the area increases with the square of the area. So if you're twice as far away, it's 4 times the area. So we're not going to worry about the 4 pi part. We're just going to be worried about the 1 over r squared part. Now this is another slide that I stole from a previous lecture. Now I have to warn you, because I didn't think about this before class, I probably should have, that in all of these slides, r and d are the same thing. It's the distance. So you can talk about the distance as a radius, or you can just call it a distance. And I should have been more consistent, but I wasn't thinking about that. I just threw this together when I realized I needed it for class. So r and d are always going to be the same. We're talking about r squared, we're talking about d squared, that's always the same thing. And the other thing is intrinsic brightness and intensity and luminosity. I'm using my mouse now. I'm not sure how well that's working. Those are all the same thing as well. And so you'll see it abbreviated sometimes as L for luminosity. But it's also the same as intensity on your handout for today's lab. And we're going to be always using the units. And I put units usually in square brackets. The units for this is going to be watts today. We're just going to be using light bulbs. And so if I talk about a 60-watt light bulb, I mean its luminosity or intensity or intrinsic brightness, all of those terms are equivalent. It's 60 watts. All right. So here we have the intensity or intrinsic brightness that is measured in watts. And then here we have the radius or distance, and that's measured in centimeters, right? So if we square that number, it's going to give a centimeter squared, which isn't the standard units, but that's what we're going to be using for today. And so that means that flux, which is how bright things appear to be, is going to be in units of watts per square centimeter. So that's the only equation we're really using in this part of in this lab, but we're going to be doing several different things with it. And the first thing we're going to be doing is we're going to measure both the flux and know the luminosity stays the same, and we're just going to graph the flux getting bigger from distance. We're going to measure flux, we're going to measure distance, and we know luminosity stays the same. And we're just going to see that those two are related to each other by 1/square relationship. So that's the first thing we're going to do. The next thing we're going to do is we're going to calculate flux if we know the wattage, that's the intensity, and we measure the radius. So if it's a 60-watt bulb and we're 10 centimeters away, it's going to be 60 divided by 10 squared. And that will give us the flux in watts per square centimeter. It'll be a small number because watts per square centimeter is not going to be a big number. It'll be a number much less than 1. So if we have two bulbs and want to compare the brightness, we can measure both wattages, or we know both wattages. We do both distances, both R's, and we can get two different fluxes. And you can compare the two different fluxes with a percent difference. Just like I mentioned on the previous part of the lab, percent difference is always going to be difference over average times 100%. Now, if you know both distances, but only know one wattage, the other bulb is unknown, then we calculate the flux of the first bulb, which is on your worksheet, and then we just assume, and I know it's not always safe to assume, but we're going to do it this time. We're going to assume that both bulbs have the same flux, that we've measured them to have the same flux. I have a device here that can show us when the fluxes are equal. And if we assume the same flux, then we can take the same equation and solve it for intensity. And so that gives us the unknown intensity of the second bulb is equal to the flux that we measured from the first bulb times the radius squared to the second bulb. And so you have to be careful that you're using the right radius. When you're calculating flux with these unknown bulbs, we use the wattage and the flux of the known bulb, which will always be 60 watts. When we're calculating the wattage of the unknown bulb, we're going to use that flux calculated from the 60-watt bulb, but we're going to use the other distance, the distance that we measure to the unknown bulb. And once we get to that part of the lab, hopefully it'll all make more sense. So I'm going to stop sharing this, and I'll put this on Moodle at the end of this so that you can refer to this when you're doing the calculations. You have pretty much the rest of the day, or even, if you want to, until the weekend to get this worksheet in. Since some people are doing it today, some people are doing it Monday. I'm not going to really be looking at them until Monday or even Tuesday. Okay, so I'm going to get out of that. I'm going to unshare that. And so now you should be back to seeing me. So now I'm going to, well, first thing I'm going to do is I'm going to go turn out the lights because with this lab is done in the dark. So let me go do that. This stuff moves where I want it. I'm going to switch to the other camera view. Whoops, that's not what I want to do it. So I'm going to here the camera view. Okay. Everybody seeing the other camera now?
Yes.
Yeah, you should be seeing the light. This is a light sensor. It's hooked up to a digital recording device. We're just going to be reading the numbers off the screen. I got to turn off the ceiling lights. Let me see if I can do that. Okay, so you can't tell, but now the only light source in the room is my 60-watt light bulb. Ah! And this light sensor is staring right at the 60-watt light bulb. And the sensor is connected to this device called the GLX, and it's registering the flux. Now, don't worry about the units here, because the units on this one is just percentage of its maximum value. So it's just going to be a number between 0 and 99.9. And it doesn't have any physical units we can really associate it with it. That's okay, because we only care about the relative change in the number. And so we're going to, right now we're not at the right distance, and so don't worry about that number. That's just an example. What I will show you is, as I move the sensor around, if I move it farther away, that number gets smaller. If I move it closer to the light, that number gets bigger, right? So what I'm going to do, I'm going to take 10 measurements, and you're going to write these down on your worksheet. So the first one, I'm going to get this lined up so that the front edge of my carrier here is at 10 centimeters. You all see that? I'm at 10 centimeters at the front edge. Very close. And I want to make sure that I'm lined up so that the bulb, I'm staring right at the bulb. Sorry, I washed it all out there. So I'm staring right at the bulb. So that should be my biggest number. All right, I'm a little too close. So I'm going to try to back this off so that my 10 is not going to, because it was pegging out my meter. There we go. So now this is at 10. And my, I think it's close enough you can read it. And that's at 99.4. Can anybody read that? So we're 99.4. I have a short cord on this camera, so I have to move my computer around on a chair. So it's switching back and forth. We'll call it 99.4 at 10 centimeters. And then I'm going to come over here, and I'm going to move from 10 centimeters to 20 centimeters. Make sure I'm still lined up with the light. So 20 centimeters, now the value is 39.5.
Is that what we're gonna write in the other
Yeah, there should be a
part
table
of distance and brightness?
Let me find the let me find that right quick. I'm gonna set this here for a moment.
So it's 10 centimeters on distance and brightness 99.4.
Right.
Okay.
And then the second value should be 20 centimeters of distance and 39.5 for the so that should be on the second page. It should be this table, right? So you're filling out distances and brightnesses. We're going to do 10 total. So there's 5 in this column, 5 more in this column. So you should have 10 numbers total.
There we go. Let's quickly.
All right. So now we're going to move 30 centimeters. Too much.
Oh, okay. So can you show me one more time where we're supposed to write the 10 centimeters and the 99.4?
So
Is
on
it in
your
the box?
worksheet, it's
Or under?
it's this table. So we'll say 10,
Okay. Yeah.
99.4. Say 20, whatever that was. I forgot already.
Yeah, I thought for a
30
second you
something.
say in the bottom. So sorry.
Yeah, sorry. Yeah, so it's the top of page 2. That's where it's going to be. And then, and so now we're at 30 centimeters, right? So we're at 30 centimeters. And our number now, if I get where I can see the screen, my number now is 19.8 is the brightness. Now we're going to move this again until we get to 40. And make sure we're still pointed right at the bulb. And now we're getting 12.3. Right, everybody got the 12.3? That was at 40. Now we're going to move this to 50 centimeters. And now we're at 8.2. So you can see how rapidly it's getting smaller. And we're only halfway there. We're going to go out to a meter. So 50 centimeters, 8.2. Now I'm going to go to 60 centimeters. Trying to make sure I'm lined up with the bulb. And now I'm at 6.5. So 60 centimeters is 6.5. Now I'm going to go out to 70 centimeters. And at 70 centimeters, I'm now at 4.8. Now I'm going to go to 80 centimeters. Come on, focus. So 80 centimeters, I'm still lined up with the bulb. And I'm at 4.0. And now I go to 90 centimeters. I'll move my computer again. So at 90 centimeters, and I'm at 3.3. And then I'm going to go all the way out to the edge of the meter stick at 100 centimeters. Make sure we're still lined up with the bulb. And now I'm at 2.8. All right, so that should be 10 different distances, 1 through 10. And that should be 10 different brightnesses. It started out at that 99.5 or 4. And then this last one is 2.8. All right, so I'm going to switch. I'm going to unshare this. Now, the next thing we want to do is we want to do an Excel graph. And you guys are going to do this later and turn this in along with your worksheet. So you just turn in the Excel file. I'm going to show you how to do it, but you're going to need to do it for yourself independently. And the lighting's kind of weird in here, but that's okay. So let me see if I can share my Excel. All right. So in my first column, and we can make it look pretty, I'm going to have distance. I'm going to have brightness. You guys see my Excel page? Somebody say yes if you can see my Excel page.
Yes.
Okay, thanks. I'm never confident that this sharing stuff works, even though it's supposed to. So you can see I put in the 10 distances. Now, I didn't write down the brightnesses because I had my hands full. So I'm going to need one of you guys to read them off to me. So 10, it was what, 99.4? And then at 20, it was
39.5.
Oops. That didn't work right. There we go. And then at 30, it was
19.8.
19.8.
19.8. And then at 40,
12.3.
and then at 50,
8.2.
at 60,
6.5.
70,
4.8.
80,
4.
90,
3.3.
100.
2.8.
Once you have all your 10 numbers or your 20 numbers in two columns like that, the easiest way to do this is just highlight everything. And then we're going to say insert chart, and we're going to choose a scatter plot with just dots. And so you can see here that we have a scatter plot, and that is showing getting dimmer with distance. What we want to know is, how much is it getting dimmer with distance? Does it really follow a 1 over r squared power law? So I'm going to right click on the data point, and I'm going to say add trend line. And over here for the trend line, I'm going to say power law. And I'm not going to be able to see it there. I got to display the equation. Let's see if I can do it from over here. Just going to pull that back. Oh, I can move that. I didn't know that. So display equation on chart. And then I can get rid of that. And so we have now is the power law equation that fits that data. Now it always makes it too small to read. So I'm going to right click on that, say format trend line label. And I'm going to go up here and make it bigger. So the only number we care about is x to the power. We care about that power because that is what's supposed to be 1 over r squared. Now, saying 1 over r squared and saying r to the -2 power is equivalent. So we expect this to be a -2, but it's not, because this is the real world and we have other sources of light like reflections. We have my sensor maybe wasn't always pointed right at the center of the bulb, and lots of things that make this a real world thing and not equal to the theory exactly. But if you notice on your worksheet, there is a space here under the where you have all the data, where it says exponent of x. And so the answer there is going to be -1.582. Now, as I mentioned, in order to get full credit for this, you have to do this Excel page yourself. But I've already shown you exactly how to do it. And so you shouldn't have too much trouble duplicating this. Ideally, you'd want to give it a chart title. You'd want to label the axes with distance and brightness. Distance is in centimeters, brightness is just a percentage, so don't worry about units on that one. So you want to make it look nice. Another thing you can do is you can, let me get rid of this thing. We can right click on the chart and say move chart and say move to a new sheet. And that way it makes it a full page, which is nicer. And so you can see from these dots that they don't all exactly touch the line, but they're pretty close. And so that's just verifying that 1 over r squared law actually works. So I hope that made sense to people. Now, the second part of the lab, we're going to use more or less the same setup, but we're going to be using 2 light bulbs instead of 1. So I'm going to have a second. I'm going to get rid of my sensor because I don't need that anymore. Turn him off.
You see? Yeah.
And then I'm going to plug in another light bulb,
See?
which makes the lighting in here even more weird. I'm going to set the light bulbs to be exactly 1 meter apart from each other. And I'm going to take this thing, which we call a wax photometer. Basically, it's 2 pieces of paraffin wax with aluminum foil in between and just rubber band holding it together. And the reason we use this is because it's a very good way for us to measure relative flux or how bright something appears to be. You can see as I hold it in my hand, if you look at my picture, hopefully you can see that one side appears very bright and the other side appears very dark. And if I turn it over, you can see it's still the same. The side closer to the light bulb is bright, the side farther away from the light bulb is dark. So if I put this in between my 2 bulbs, it'll show me which bulb I'm getting more flux from. So I'm going to share the other camera right quick.
Got it. No.
All right, so you see in the other camera view now, right?
Yes.
Yes,
Got
okay.
it.
So, and I have to get close to it for the contrast to be good enough. So you can see here that I'm definitely closer to this bulb than I am to that bulb. They're both 60-watt light bulbs. And you can see that I'm also closer in distance. I'm at like 76 centimeters. So as I push this closer to the middle, you should see that the dark side gets brighter and the bright side gets dimmer until they pretty much start looking the same, right? So now they look pretty much the same. And you can see that I'm about halfway. If I keep going, then the right side gets darker and the left side gets brighter. And we know that we're closer to the left-hand bulb because we're getting more light. This is basically measuring flux, right? So I'm measuring relative flux. So what we want to do, the 60-watt version is really just to practice, or in this case to demo, since I don't need to practice. And so it's just because we know that the middle of the meter stick at the 50 line, that's where it should be, they should be equal brightness. And so we're on the left side, you see the left side brighter. We're on the right side of 50, we see the other side's brighter. Now, without looking at the meter stick, I'm just going to look at the camera, same as you, and I'm going to try to decide where the middle is. So now we're too far that way. And now we're too far that way. The way I've often found that it's easiest to be able to tell, because there's a range of distances where you can't really tell the difference in brightness between these 2 guys. And so the easiest thing to do is find the places where you can tell and then split the difference. So we can just barely tell there. And we can tell, whoop, that's a little too much. We can tell about there. So from here to here, we should be splitting the middle. And so if we go in between the 2, oh, that doesn't look good. So it's really hard to get the camera where it can see the difference because it wants to change the brightness. So there we're still a bit too far on one side. Now it looks pretty much the same. And I wasn't looking at the meter stick. I looked down, and you want to go by the seam right in the middle of the between the 2 pieces of wax. So that seam, we go down, and it's at 50.5 centimeters, 50.5 centimeters. So we did pretty darn good. And so on your worksheet, let me set this down for a second. On your worksheet, we're doing the 2 60-watt bulbs. It's called confirmation. So the distance to the first 60-watt bulb is going to be, whoop, you can't see that. Hang on. Distance to the first 60-watt bulb is going to be, if I can get it to focus. Well, there we go. Distance to the first 60-watt bulb was 50.5 centimeters. Distance to the second bulb, since we 100 total, it's just going to be 49.5. So 50.5, 49.5, and we're going to calculate the two fluxes. So the first flux will be 60 divided by 50.5 squared. The second flux will be 60 divided by 49.5 squared. And they'll give you slightly different numbers. And so we'll be able to do a difference, a percent difference, where we take the average divided by the difference times 100. That'll give us a percent difference there. It should be a fairly small number for this one. Now, the second thing we're going to do is we're going to switch out one of the 60-watt bulbs with a 40-watt bulb. Now, I'm always going to leave the one on the right as the 60, and I'm going to be changing out the one on the left because that's where all my spare bulbs are over here. So it's just more convenient for me. So there's no special reason to do one over the other. So I am going to change out the bulb. And in case you're worried, I'm wearing gloves, so I'm not going to burn myself, even though I'm just wearing a lit bulb. When we do this lab, normally there's always at least one macho guy that's got to try to do it without turning off the bulb or using his glove. And he usually burns his fingers, and we all laugh, you know, so that's always fun. Okay, so now we have a 40-watt bulb, and you can't really tell yet, but I'm getting closer. You should be able to tell. I haven't moved this, right? I haven't moved this guy. I haven't moved either one of the bulbs, but now one of the bulbs is now 40 watt. And you can see that with a 40-watt bulb, we're no longer equal, right? Because even though we're the same distance, the 40-watt bulb has less intrinsic brightness, less luminosity or intensity, and so less wattage. And so it's not giving us as much light at equal distance. And so I'm going to move this a little bit towards the 40 bulb until it appears equal again. And again, the way I can usually try to see it is I'll go a little bit past until I can definitely see a difference. Go a little bit past the other way so I can definitely see a difference, and then kind of split the difference there on distance until I am happy with the relative brightness. So I'm going to tweak it just a little bit. Nope, that was the wrong way. Let me go this way. That looks pretty good. Maybe a little bit towards the... It's actually, I think the camera is actually more sensitive than my eyeballs. So I'm actually get better numbers now than usual because the camera is actually a little bit more sensitive than my eyeballs at seeing the difference in brightness. Okay, so that looks pretty much the same. You have to be careful too because the dimmer bulb will be a different color. So the dimmer side towards the dimmer bulb might be a little bit redder, and this one might be a little bit more towards the white. And so you have to be careful that you're not looking at color. You have to be colorblind on this and just look at, so that looks pretty good. So I'm going to go down here and see what I'm looking at. It looks like 45 centimeters is right at that seam. And you may think it should be 40 centimeters. This is a 40-watt bulb. Remember, the distance is squared, so it won't be that simple. But we can still figure it out. And in this case, since we still know both bulbs, we're going to put the distance to the 40. We're going to say that was, what did we say? We said that was going to be 45. So the distance to the 40-watt bulb is 45. The distance to the 60-watt bulb is 55. And then our fluxes, we do the same thing. It's going to be 40 over 45 squared. And this one's going to be 60 over 55 squared. That'll give us two numbers that are hopefully similar. And then we can do a percent difference, which is just the difference divided by the average times 100 to give us a percent difference for there. So that is 2A and 2B. the last three things we're going to do are our three unknown bulbs. And I'm just calling them small, medium, and large because we don't know what their wattage is. That's the point that we're trying to figure out. And so we're going to start out. I'm going to replace the 40-watt bulb with my unknown one. I'm going to put this back here. And I'm going to remove my 40-watt bulb. And I'm going to put in this. Okay, so now I've got a much dimmer bulb, and you can see even before I get close, you can see that it's much, much dimmer on the wax. And so I'm going to have to get pretty darn close to this Peaslee little bulb in order to, and again, it's also much redder. So we're going to have to be careful that we ignore. Now I think it's definitely getting brighter. Even though it's redder, it's still brighter than the other side. So I'm going to back it off a little bit until, again, you'll notice the color difference. One side is definitely redder, and one side is a little bit more blue. But brightness-wise, they look pretty good. And so I'm going to look at that line. I'm going to go down, and it looks like 27 centimeters. So 27 centimeters is the distance to the unknown one bulb. So if I go back to my worksheet and I say, okay, the distance to the unknown bulb is 27 centimeters, which makes the distance to the 60-watt bulb 100 minus 27, right? So that should be what, 73. So 73 centimeters to the 60, 27 centimeters to the unknown. But now we can't do both fluxes separately because we don't know the other wattage. And so we just have to assume that the fluxes are the same. Remember the first two, we figured out both fluxes and found a percent difference. That was just seeing how good our method was, because we expect those numbers to be fairly small. Now we are going to have only one flux that we know, so we have to assume they are the same, that these numbers worked out similar, and these differences were small. And they may not be that small. This lab isn't the most accurate in the world. I mean, our primary measuring device is a chunk of wax, right? And so it may be that some of these percent differences could be, 20% or more. And so we may not be doing that great, but we should get in the ballpark. And so we use our 60-watt bulb. So 60 divided by 73 squared is going to give us the first flux. If we assume that flux is equal to the flux of the other bulb, or the unknown bulb, because the wax was the same brightness, then we can solve the equation for the wattage. And I don't have it written down here. I showed you on the PowerPoint, but just to remind you, if you know the flux, the wattage is going to be the flux times the distance squared. So it's going to be the unknown distance squared, which is going to be the 27 squared, times the flux that we got from the 60-watt bulb, and that's going to tell us the wattage. Now, we don't know what this wattage is going to be until we work out the numbers. But because it's a pretty dim bulb, I'm going to guess, I'm sorry, I was on the wrong line. It should be up here, bulb 1. I'm going to guess it's going to be somewhere in the 5 to 15 watts. Okay? I don't know if it's going to be exactly that, but it should be somewhere in that ballpark. That'll just let you know that you're doing things right. You should get a pretty small number that is reasonable for a relatively dim bulb. I know you can't really tell, but it's way dimmer than that one. So now I'm going to switch out my small bulb for my medium bulb. So we're going to unscrew this guy. And I'm going to screw in my medium unknown bulb. It's just a regular bulb, so it's probably a 40 or a 60 or an 80 or something like that. So looking at the wax, we see that we're going to need to go back towards the middle because it's brighter. So we're going to keep going until it looks pretty much good. So if I go a little bit more, that one's dark. Go a little bit that way, that one's dark. So right in the middle here, I think that, well, let's go a little bit that way. Nope, a little bit that way. Okay, so that looks pretty good. So we got a bulb over there, we got a bulb over there, and we're here. And so I'm gonna go from the seam, I'm gonna pan down, and we're at 42 centimeters, which is pretty similar to where we were when we had a 40-watt bulb. So that may be, you know, a 35, 40-watt bulb, somewhere in that range. But we're going to do our calculations in order to know for sure. So going back to our sheet, I have to move it out of the way because it's white and it'll reflect and mess things up. So now we're at unknown bulb 2. So it's 43. So the distance to unknown bulb 2 is 43, which makes the distance to the 60-watt bulb, it's always going to be 100 minus the first number. And so 100 minus 43 is going to be 57, right? So 57 to the 60-watt, 43 to the unknown 2. And we're going to do the same exact math. 60 divided by 57 squared gives us the flux. We assume that flux also applies to the other bulb, and so we multiply that flux by the unknown distance squared, which in this case was our 43 squared, and that will give us our second unknown wattage. And we're going to guess that it's going to be somewhere in the 30 to 50 watt range. We don't really know yet, but once we do the math, we're going to assume that that's going to be somewhere in the 30 to 50 watt range, which is a sort of normal sized bulb. Now, the last bulb we're going to do is our large bulb. And I'm going to show you this one before I plug it in, just so you can see how impressive it is. This is my large bulb. This is a big honking bulb. So we're going to hook that puppy up, and it's going to be like the sun in here, at least for me. Okay. You can always tell when I'm normally doing this lab, you can tell when people get to the bright bulb because everybody starts going, oh my gosh, it's so bright. And I usually put on my sunglasses, you know, just to look cool, but I forgot to bring them in from the car today, so don't get to see that. Whoa! Made a pop sound. It didn't die. That's good. I've only got a few of these super bright bulbs, so I don't want them to die if I can help it. And you can see it's so bright, it's actually casting a shadow here. So it's way, way brighter. So I'm going to move this towards the 60, a lot, towards the 60. And eventually, once I get pretty darn close to the 60-watt bulb, then it's going to start looking a little bit more even. I get my computer a little bit closer and run out of cord here. All right, so still looks like it's maybe a little bit brighter towards the unknown bulb. That looks pretty good. So that looks pretty good. One thing I always have to warn students about is when you're moving this, make sure that your hand is down low. Because you see, if a shadow passes over, this is just my hand. If a shadow passes over that thing, it really makes a big difference. So you have to be careful. This appears to be pretty darn good. So I'm going to pan down. And where were we? We're about here. Things are getting wonky here, but I'm going to call that 72 centimeters, maybe 71. To this side. I'm going to call it 72. So 72 centimeters. So going back to our worksheet again, one last time. Our distance to the unknown bulb now is 72 centimeters. The distance to the 60-watt bulb is going to be 28 centimeters, right? So 28 centimeters to the 60-watt bulb, 72 centimeters to the unknown 3 bulb, the big bulb. And so same exact routine. We're going to take 60 divided by 23 squared, or sorry, was it, no, 28 squared. 60 divided by 28 squared is going to give us the flux. And then we use that flux times the 70, what was it? 72 squared. And that will give us the wattage. And this is a really, really big bulb. So I'm going to guess that this is going to be somewhere in the 250 watt range. Again, I don't really know. I don't know what the real wattage of this bulb is, but it's going to be much more than 100 watts. Probably somewhere between 200 and 300 watts. It could even be more than 300. I don't know. So that's going to be a pretty big number. All right. So that's it. So we've completed today's lab, and all that you're expected to do is give me the worksheet on Moodle. So the stuff we did first and the stuff we did second, all these numbers should be filled out, all the calculations should be done. This plus that Excel file where you type in those numbers like I did, and you do the exponential graph, and you find that exponential curve by doing a power law fit. That Excel file plus your worksheet, either completed as a Word document, or if you fill it out on paper and take a picture or scan, and whatever way you can do it, get that to me and try to get it in the next couple of days. But like I said, I won't be grading them until after the Monday lab because we're doing the same thing on Monday. So don't sweat it too much. Remember, if you haven't already taken the test today, you have to complete the test by midnight. You have 90 minutes, but it's going to close at midnight, whether you're done or not. So don't wait till 11:30 to start it, or you only have 30 minutes to take the test. All right. Any final questions before we call it a day?
Could you show how to do the graph on the sheets again?
Yeah. Let me switch back to the Excel right quick.
All right. Thank you.
So in Excel, you're going to have the first column should always be your X values, your horizontal values. In this case, that's distance. So your first column is always going to be distance. I just have it 10 through 100. Notice that you don't put any units or anything else if you want it to graph, because if you start putting units or labels, it's going to treat it as text rather than numbers. And so we want it to treat it as numbers. And so I have just the 10 numbers, 10 through 100. And then the second column Column B is going to be my brightnesses, those 10 numbers that we wrote down. And then once you have that, you just highlight all the numbers, not the labels, but just all the numbers, and say insert, and then go to charts. And there's one that just got a bunch of dots. It's called a scatter. And I just picked the first scatter, and it does that. So, and then once you have it, you can right click on any data point and say add trend line and do a power. There's a choice called power, right? And then you have to turn on the equation in order for it to say display equation, and it'll give the equation. Now, Excel is really good at giving you the equation in a terrible location. It's always on top of stuff where you can't read it, and it's always too small to read. So you'll have to move it, and then you'll have to make it bigger. And I think you can either have it highlighted, and I think you can just change it directly. Yeah. So once you have it highlighted, you can change the font size, make it, that's too much, but you can make it as big as you want. And putting it on its own page is optional, right? But you can say right click, move chart, and it'll put it on its own page. And then if you want to add labels, X and Y labels, you can just go over to, where is it? Up here under design, add chart element. And you can do things like do an X-axis label, do a Y-axis label. So you can add all those things by just selecting them here and then filling in the numbers down here. All right.
All right. Thank you.
Any last questions?
On the last equation. Sorry.
You might have to turn on your speakers if you're getting
I
feedback.
got about 400.
You got 400. Okay. Well, I did say it was going to be a big number, and that's not actually that surprising. So I was expecting to be quite that big, but I wouldn't say that was beyond the realm of possibility. So yeah, if you're getting 400, that's probably still okay.
Okay.
The other numbers were kind of in the ballpark of what I was saying.
Yeah.
Okay, good. So yeah, everybody should get answers that are fairly plausible for the size bulbs that we were using. Remember, these are wattages, and so it should be reasonable numbers. I said 5 to 15 for the first one, 30 to 50 for the second one, and it sounds like the last one's going to be around 400. Which I knew would be big. I didn't quite realize it would be that big without doing the math myself, but that's not super surprising. So that's not a problem.
So
right. So
chart. Do you just want labels? Do you want to make
chart? Yeah, if you could just put a label on the X called distance and a label on the Y called brightness. That's really all you need to do, and then maybe a chart for a label for the overall chart that just says, brightness versus distance.
Can you say the labels one more time?
Distance for the X and brightness for Y. It's the same as what's labeled on your worksheet. So on the worksheet it has where you fill out the data, it's labeled as distance and brightness. That's really all you need.
Okay. And then can we attach the chart to the document? The Word document, just upload that together?
You can, but the upload on Moodle is set up to allow you to upload up to 3 separate files. And so it might be easier for you and for me if you just upload it as a separate file rather than trying to attach it or embed it.
Because you can basically, what you can do is just copy, like right click and press copy and then just paste it on the Word document. And
Yeah, you can embed Excel charts in Word, and you can, but you don't have to. You can just give me the Excel file separately, and it should allow you on Moodle to upload up to 3 files.
Okay.
Which in this case should be enough, because at maximum you're going to have, even if you're scanning your worksheet, you'll have the front page, the back page, and the Excel file. So you shouldn't ever need more than 3. But if for whatever reason you have more than 3 files you need to upload, let me know and I can change that. But 3 should be enough, I think, for this assignment.
Okay.
All right, anything else? All right, so I guess that we'll call it a day, and I'll see everybody for class next Tuesday.
I have a question.
Oh yeah.
Are we gonna have like bonus tests or something?
Are we gonna have what on the test?
A bonus?
A bonus for the test?
Yes.
I don't have anything planned for the test specifically, but there will be some additional chances to get bonus credit for the class. One of them that I don't know if it's going currently, but you may remember we talked about before spring break was that that one where you look at the night sky. What was it called? Globe at Night, right? The
Yeah.
Globe at Night campaign. I know there was one for March and there was one for April. Even though we're all scattered across the place now, that campaign is still going, and that bonus credit is still available. So that would be a good chance to do that.
Okay.
So I know that my my normal bonus towards the end is to have students come to some of the physics student presentations. But since that's not going to be possible, I'll think of alternatives. So I'll try to make sure that you guys have the same number of bonus opportunities as you normally would if we were going to be on campus. Because since we're not really going to have the opportunity to do the student presentations, then I'll come up with something. Although, now that I'm thinking about it, we may end up doing the student presentations as you know, on here on Microsoft Teams. And so it may be that you logging in electronically to watch the presentation will count instead of you physically being in the room. So that's a possibility, but I'll try to come up with some other ideas as well. All right, so you won't be shorted on bonus, I promise.
Okay.
All right, anything else? So I'll see you guys on Tuesday. Bye.